We just learned a couple techniques that we can use to solve polynomials. And in doing so, we learned that we can find the factors of polynomials just like we can find the factors of numbers. When we do prime factorization, we take some number and split it up into factors until we are left with only prime numbers. That begs the question, are there prime polynomials? The answer is yes, and if we have a complex polynomial, it may be prime, meaning it can't be factored, or it could be that we can split it up into a number of different factors. It may not always be easy to tell whether a polynomial can be factored. For example, x to the sixth plus 1 is prime. It can't be factored. But x to the sixth minus 1 is not prime. It can indeed be factored. So we need a way to test whether a polynomial is divisible by a particular expression or not. That technique is called synthetic division. It works a lot like long division, which we learned at the beginning of this course, except that we are using algebraic expressions instead of numbers. This will come in handy if we have something like a cubic or quartic equation, and we know one of the zeros. Let's say we are looking at x to the fourth plus x cubed minus 11x squared minus 5x plus 30, and we want to see if x equals 2 is one of the solutions. If it is, then x minus 2 would be a factor, and that could allow us to simplify the expression. The way we will test this is as follows. Let's make two lines at a right angle like this, and in this top row, we will list only the coefficients of our equation. Then we want to test to see if 2 is one of the solutions. So let's put a 2 to the left over here. Now we take the first coefficient, in this case a 1, and drop it down here. Now we multiply by the 2 and put that here. Now we can add these together to get 3 and write that here. Again, we multiply by 2 to get 6. Adding to negative 11, we get negative 5. Then we multiply to get negative 10, add to get negative 15, multiply to get negative 30, and finally we add to get 0. The fact that this is a 0 right here means that there is no remainder from the division, which means that 2 is a solution, and therefore x minus 2 is indeed a factor of this polynomial. These resulting numbers here tell us the coefficients of the polynomial that remains after dividing by x minus 2. We just have to understand that what is left will be of a degree that is 1 less than the original polynomial. So since we started with a quartic, the result is a cubic. We can simplify this to x minus 2 times x cubed plus 3x squared minus 5x minus 15. If we wanted, we could continue factoring from there until we have nothing but binomials, and therefore all the possible solutions. Say we continue with this one and try to see if negative 3 is a solution. We would perform the same algorithm as before, dropping the 1 down, multiplying to get negative 3, adding to get 0, multiplying to get 0, adding to get negative 5, multiplying to get 15, and adding to get 0. Once again, with a remainder of 0, we see that negative 3 is indeed a solution, and x plus 3 is therefore a factor. So leaving the x minus 2 as it is, we can factor this cubic term further to get x plus 3 times x squared minus 5, which we get from the coefficients we just calculated. That last bit is easy to solve in a separate equation. We just bring 5 over here, take the square root, and we get plus or minus root 5. That means we have successfully found all 4 solutions to this original quartic equation, and those are 2, negative 3, root 5, and negative root 5. So this is the best